In this video, we're going to take a look at a couple other new shortcut rules that we can kind of start to add to a big list of shortcut rules that we will develop to make calculating derivatives a whole lot easier. So I'm going to present here a fairly intuitive set of ideas. It's actually kind of three theorems all in one, but I'll box them up all together that show us how to differentiate a larger variety of functions. Let's read through this box first, and then we'll try to justify at least a couple of these. Suppose that c is a constant, so anywhere I see a c in here, just imagine a number, and f and g are differentiable functions, so I know I can take their derivatives. Okay? Then the following rules definitely hold. The derivative for any constant, that is, if I take the derivative of any number, I should always get back 0. This actually makes a lot of sense because if I'm working with a constant function, a constant function would be a function that has a horizontal line representing it, maybe something like y equals 1. And if I take the derivative of that, I'm told I get 0, because any tangent line on here is going to be identical to the function itself and would have a slope of 0, no matter what point I started at. So this is what we call the constant rule. The derivative of any constant is 0. The constant multiple rule states that if I want the derivative of a constant being multiplied to some other formula, I could instead just take the derivative of the complicated formula and leave the constant to multiply on after. I also have sum and difference rules, kind of like we had sum and difference rules when we were dealing with limit laws. This says if I want the derivative of two formulas being added or subtracted together, I can take the derivative of each of them and then add or subtract the results. Now let's go ahead and actually try to show that these derivative rules actually work beyond just this intuitive sense that we did up here in our first picture. To prove these, of course, we're going to actually have to go ahead and use the definition of the derivative to confirm that these work. So for the proof of number 1 here, I'm going to see that I'm starting with a function like y equals some constant. So I'll start here by saying, oops, let me switch colors here. I'll start here by saying, suppose that f of x, the function I'm working with, is just a constant. Could be any constant c. So then, by the definition of the derivative, I could see that f prime of x has to be equal to the limit as h approaches 0, remember, of f of x plus h minus f of x all over h. Now this is kind of interesting because notice what this is going to require that I do. This says first go to the function f and plug in x plus h. Everywhere I see an x in the formula, replace it with x plus h. Well, there are no x's in this formula, so I can't really replace anything. This first part is just going to be the function itself. And similarly, I'm going to get the function itself for the second portion up in the top. So what I'm going to end up with here is a limit as h approaches 0 of 0 over h. Of course, that simplifies down to just be the limit of 0, and the limit of 0 is 0. And so we actually have everything that we need. We can end our argument, right? The limit of a constant function always ends up being 0. It didn't even matter what the value of c was. So that's a pretty simple one to show. Well, let's take a look here at maybe something like number 2. How could I prove that if I wanted to take the derivative of a function like this, that I would actually end up with this as a derivative rule? Well, I'll start by saying, let's suppose that we have a function that looks like c times something else. Okay, so I'm giving this function the name g, and g is constant times some other formula. Well, again, then I should be able to state that if I wanted to calculate the derivative of this, I wanted to calculate the derivative of constant times mystery function, I again would just have to calculate the limit of g of x plus h minus g of x over h. That's always what I would have to do. Now, in order to be able to go ahead and simplify this down, I'll have to go ahead and see that my g of x plus h would require that I go to the formula over here and replace all x's with x plus h's. So that would leave me with c times f of x plus h. I would then have just the regular function c times f of x up top for the second portion. Well, when I look at this, this is kind of confusing. There's a lot going on here. But one thing that you might notice is that in the numerator of the fraction, there is a constant. And so I could go ahead and actually factor that constant out. I could factor it out and have could take that constant kind of off of the top of the fraction, and I would be left with f of x plus h minus f of x all over h. Notice again that I'm bringing this to the front of the fraction, and I can imagine it being remultiplied up top if I just quickly reimagine that as c over 1. Okay, so that's how I know I can put it there. But now I have the limit of a constant times something. And according to our limit laws, remember that I can always take a constant and pull it outside of my limit. And so I would just be left with this inside of my limit. But here's the crazy part. What can I rewrite now this limit as? Because isn't this limit a familiar limit? Don't we already have a way to represent this limit? Yeah, this is just the derivative of the function of f. So this can just be replaced with f prime. So I can actually see if I take the derivative of something like c times a function, I just end up with c times the derivative of that function. And so my argument is again complete. Now, the third part of this theorem, I'm actually not going to prove here, but that's actually going to be one of our deeper understanding questions that I'm going to ask you to work through in homework assignment number 4. It's not too bad, and you can use these ideas here to try to go ahead and see how exactly I'm setting it up and how I'm justifying what I'm doing in order to confirm these laws are actually true.